computer, and we're good to go.
Okay, I'm going to share my screen. Found the right one always. Yeah, I'll share my desk. Can I share my desktop? Yeah. Yeah. Where have I lost it? Here it is. Okay. Well, welcome everybody. Thanks for joining us tonight. And we want to welcome people who are new to our deep learning adventures and also some familiar faces. We're moving on from our Kaggle adventures, and we're going to start a new adventure tonight, and I'll get into that in just a minute. If you're not familiar with us, we're called Deep Learning Adventures. We've started about a year ago, and I was lucky to have begun this with my good friends George and Robert. They're going to be our speakers tonight, and I'll talk about that later. We've done several different things. We started with a Coursera course on TensorFlow, and it was a very introductory how to use TensorFlow for different types of deep learning problems. It's the specialization that we went through there. We then moved on to do some coding projects. We've done various types of study and courses in Kaggle. And we just finished up a long set of courses in Kaggle. And now we're going to go back to working in Coursera again. If you're not part of our group, we have a Slack group that is pretty active, and we welcome you to join us on Slack, and hopefully maybe George or Robert can post the invite into the chat here tonight. It's on our meetup page as well. We also record our adventures with YouTube, and for this next one, we'll have a brand new track. We have different playlists there going through our Kaggle and our deep learning Coursera courses, and we're going to have a brand new one for this TensorFlow data and deployment specialization that as of tomorrow, hopefully we'll have the first video up from tonight. So that'll be a place to look for these if you can't stay for the whole one, or you miss one of the series, to catch up with us. So what are we going to be talking about tonight? We're going to start on a specialization by deeplearning.ai that's through Coursera. It's taught by Lawrence Moroney, and we went through one of his courses before, and we're very, very pleased with him, and brought him in as an invited guest to interview. You can look back on YouTube and find that if you're not familiar with that. But this is a course on TensorFlow that assumes you know the basics of deep learning already. It doesn't spend time talking about how to model image problems or natural language problems. That's addressed in earlier courses. And here we're going to talk very detailed pragmatic about how to deploy your models, work with data pipelines, and some other specialty things that you can do with TensorFlow. This specialization is made up of 4 courses. The first one is on TensorFlow.js. As you can imagine, it has to do all about the browser. The second is called device-based models. It's about kind of edge devices, and it involves TensorFlow Lite. The third course is very detailed into data pipelines, which Ed was asking a question about earlier. And this is all about the TF.data library and how you can use it to provide pipelines and such. The fourth course is going to be more with deployment into very large systems. It has to do with TF serving and some of the other things about how you can monitor your deployments and do some of the things you might do with DevOps. We're going to start with the first course tonight, and I'm pleased to introduce our speakers. George Soto is going to present the week 1 to us, which is an introduction to what TensorFlow.js is. and we're going to see that from him. And then the second part of the night tonight, we hope to get to all of week 2, which is doing image classification in the browser. So it's the first week is more an introduction to the TensorFlow.js package and what you can, how you use it. And then the second is more hands-on deployment of it and how to do that. Week 3 in this course is dealing with how you're going to convert your models that you build in Python into JSON formats that you can then deploy out into the browser world. The 4th week will be transfer learning with pre-trained models in this world, and there's a lot of considerations in terms of the resources that you have available to you in the browser world versus what you can do on a server. So we're hoping to cover week 1 and 2 tonight, and then next week we'll try to get into week 3 and 4. Without any other questions on this, we're going to go ahead and get started, and I'll hand it over to George to begin week 1.
Just to interrupt, there was one question in the Slack. I just noticed a couple of hours ago that was posted about whether it's possible to audit the course. Let me go back and look at that.
So I'll give you, I should point out that we would really love for others to take this along with us. You can catch up to us if you haven't started. And we welcome presenters. If you want to take a week on that you thought you thought was really interesting and you want to present it, we would love you to help us present these and go through this. I believe that Coursera still lets you audit courses for free. That means you'll be able to watch all the videos that are in that week's data. You will not be able to do the exercises or the quizzes. At least that's when I've audited in the past what they restricted. And then you won't get the certification or the certificate for completing the specialization unless you choose to sign up and pay.
That's been my understanding in the past. I'm not sure it's still the case with Coursera.
Yeah,
so I'd invite anyone present here if you happen to know the answer to that.
Yeah, I think that's still true. I was a beta tester for this course a while ago, and I was actually auditing it. And the only difference is when you audit it, you're not allowed to take the quiz or submit the graded exercises, but you can look at the videos and everything else.
Yeah.
So I was looking into that because I'm not that interested in getting a certificate, but it seems that some Coursera courses you can do that audit with, and we've done it before, but I couldn't find it on this one, the option to just audit. They let you do it for 7 days free. I don't, and did anybody else find it a true audit, a complete audit? Maybe not then.
Okay, well that does well, you'll have to go through it with us then, I guess.
Sometimes if you the advanced specialization allows you to audit. I'm not too sure about this data science one or the data deployment one.
Okay. I will point out that you can apply for financial aid through Coursera, so that if you sometimes have to wait a little while for them to do the approval. It won't be immediately, but if that's another option that I would say encourage you to look at.
I think sometimes you can, if you look at the individual courses, those you can audit.
Okay. Yeah, we'll have to do some. We may want to send support a message and see what the options are. George, I'll go ahead and stop my share if you'll take over.
Perfect. Thank you. Awesome. Welcome, everyone. Thanks for joining us. Let me show my screen. Cool. Thank you for the introduction, David. Thank you, everyone, for joining us. So Robert and I will cover, as David mentioned, the first 2 weeks of course one. Course one has 4 weeks, and really give you some introduction on TensorFlow.js, and we'll build some simple networks together that will be trained and do inference as well on the browser, and we'll do some cool projects in the end. Just a quick intro. Our shout out to TensorFlow.js. It's a library written in JavaScript, as you can imagine, from machine learning. We've seen TensorFlow from the Python perspective. We've used notebooks, we used Colabs, all our Kaggle adventures. Most of them have been in Python. So this is now an interesting model for us. We were switching gears. We're looking at it from a browser perspective, as well as from another platform like Node.js, where you can deploy models in different platforms. This TensorFlow.js, TensorFlow.org/js website has some cool examples. And the good thing is that since this is running on your browser, you can do some cool projects. Like you can have access to your audio, your mic, you can have access to your camera, you can have access to your mouse and things like that. So making projects a little bit more interactive than before. So that's a new plus. In terms of what do you need to follow along or do some of the projects with us, again, I'm not sure if you're able to audit. Maybe sending an email to Coursera might be helpful. I'm not sure. I'll ask some of the other contacts that I have with Coursera. Maybe for some reason this is not available for audit, which is it used to be. It used to be that you could audit every course. But in terms of other resources, you just need a browser, ideally Chrome. Chrome is very easy to use and also has a developer tools option, which we'll use extensively to look at what is happening under the hood. We're also going to use a Chrome extension called Web Server. In Python, anything that we wanted to do, if we wanted to access files, we wanted to access text, if we wanted to access images, we did that through the file system of the operating system we're running on, be it Mac or Unix or Windows. Excuse me. Here, since everything is in JavaScript, everything is running on our browser. Any file that we need to access to, be it text, image, or anything else, we need to go through an HTTP request. So that means that we need to have a web server responding to our HTTP request and serving any files back to our application. So very easy to install too. It's available on this Chrome app. It's called Web Server for Chrome, and you'll see how easy it is to start. And then in terms of editor, this website this course recommends brackets. I think as of now, brackets is not supported anymore. They're recommending using other editors like Visual Studio or other ones. Personally, I use Atom, A-T-O-M, but any other browser would do. This is basically just to look at HTML and JavaScript code. So those are the three resources we're going to need for this course. And also, I wanted to mention that this course comes with repository of examples and exercises, and I'll post that right now in the chat. So if you go under TensorFlow deployment, there's also TensorFlow in practice, which we've covered in the past. You'll see a folder for each course. TensorFlow.js is the first one we're going to cover, and then broken down by weeks. And if you look at examples, you're going to see some of the examples that we're going to look at. The exercises are incomplete, as you would imagine. So when I cover the exercises portion of it, I'll refer back to this repository for us to look at. Cool. And the last thing before we start is this concept. You'll see this new concept in JavaScript. Before in Python, whatever we did was, especially using notebooks, we executed a command. It was synchronous. We had to wait for it to complete. Then we could go to the next cell. Then we could go to the next cell. Then we could go to the next cell. In modern web browsers, they're so advanced that when you call a function, that function can run what is called asynchronously. So JavaScript has tools for us to basically work with such asynchronous functions. And asynchronous means that that function will run on a thread in parallel with other threads or with other functions. So you really have to think about parallel programming and so forth. It's useful because that means that your browser is not locked or it's not using all its resources on only one function. It can do multiple things at a time. But also introduces some interesting challenges in terms of multiple programs or multiple functions trying to access the same resources. Cool. With that said, our very first model will be a very simple one, and we might have seen this from the past. And I'll jump right away to the HTML part of it, and I'll zoom in a little bit so you can see. So we'll work a little bit with code this couple of weeks. This concept is very code heavy, so if you're already familiar with JavaScript, then great. Otherwise, I'll try my best and explain what is happening here. So for this first exercise, we're looking at an HTML file called first.html.html. It's an HTML file, so it has an HTML block, start, beginning, and the end. It has a head, which there's nothing in it. And then between head and body is where you would install your JavaScript code. But before I go to the JavaScript code, this file only has a header, and this is the content of the header and nothing else. So if I open it in a browser, it just says first HTML.page. If I want to look at the page source, or even better, let me close this. If I want to look at, so in Chrome, if I want to look at the console or the output of this page, what is happening under the hood? If I go under more tools, under more tools, developer tools, you'll be able to see not only the source code, but also the console of what is happening here. Okay, I'll minimize this for now. So let's see, what are we doing in this very simple HTML page? So all the content that we'll be looking at is within this script/script block here. So the first thing we're doing is we're importing this TF.js library, which is the TensorFlow JavaScript library from TensorFlow. That will give us access to anything in terms of TensorFlow related to model training, accessing data, doing predictions, and so forth. So the language we'll be using is JS, and this is where we see that first new concept that I mentioned before, that we're creating a function called doTraining. It expects a model, and it's an asynchronous function, meaning that it will try and run in parallel while our browser is doing other things. It's accessing maybe other websites, or it's pulling data from the internet and so forth. Within this asynchronous function, we're going to create a new variable. This is how you create variables in JavaScript, called history. And that will be the output of this other inner model method called model.fit. And this model is available as an input. So it's giving as an argument, and we'll see it here how we use it. So we have a model as an input, and we'll see how we define this model and what does it do for us. Maybe I think it would be better if I start from the bottom. I usually find it easy in JavaScript code to really understand what that happens. So maybe let's okay. I'll continue for now. So we have a model as input. We still don't know how this model is defined or what weights and biases it contains, but for now, let's assume it's a simple model for us, and let's assume also that we have access to what is called the training data, the X's and the Y's. And we want to do some fitting. We want to basically create a model that fits the X's to the Y's. And what are these X's? So these X's are simply a list of elements. So in this case, -1, 0, 1, 2, 3, 4. And the Y's are the corresponding mappings from X to Y, -3, -1, something, 3, 5, 7. This simple example is trying to introduce a very basic mapping of X to Y, and the relationship is Y is equal to 2X minus 1. In the course, there's a slight typo here from one of the elements. So let's say, for example, for 0, 2X is 0, minus 1 is minus 1. For 4, 2X is 8, minus 1, 7. In the course, they have a 2 here. It should have been a 1. Not that it is super important. It's just that your data now is non-linear. This is a 2 instead of a 1. So how do we define our input here in TF.js? We define it by what is called TF.tensor something, and that something could be a 2D, 3D, and so forth. So by TF.tensor 2D, we expect 2 inputs. One is the actual data as a list, and the other one is the size or the shape of the data. In this case, it's 6 elements. It's one row of size 1 each, so it's a 6x1 list basically. Same with the Ys, we have 6 elements. Each one of them is a single item, so it's a 6x1. And we only have one such list. That's why the shape is 6x1. So this is our X's and our Y's. Let's look a little bit now, what kind of model can we build that maps these X's and Y's? But before I do that, let me just visualize these X's and Y's for us to see how they look like. So this is the first mapping that we saw where the 1 was mapped to a 2. You see it's not perfectly linear, or it's not linear. This is the right linear one. So it's basically a line, and we're trying to build a model that only has 2 variables or 2 unknowns, the weight and the bias, right? So y is equal to wx plus b. We need to figure out what is w and what is b. So our goal is to build a network that approximates w and b as close as possible. So basically trying to fit a line through these data points. Cool. How do we do that in TF.js? So we're going to start with a sequential model, and most of our models, if you remember, all of them in the past have been using this sequential API, our method call. In TensorFlow.js, we start the sequential model by invoking this method, TF.sequential, and that model now has additional methods that we can use. So you can do add. For example, in this case, we're adding a layer. And what is that layer? It's a TF layers dense. It's a dense layer, a regular dense neural network. It only has 1 unit. We only need 1 input or 1 output, sorry. And the input shape is only 1 because it only takes 1 number at a time. It takes 1x and it tries to give its corresponding y. So its goal is to take -1 and give us -3. If we give 0 as input, it should give us -1 and so forth. So very simple, 1 neuron network here. We'll compile it using a loss optimizer and metrics as usual, as we've seen in the past. Here we're interested in the square distance between our output and the actual output. So we're going to use a mean squared error loss function, and our goal is to minimize that so that our prediction, so let's say we predict -2.5, but the actual label is -3. We want to minimize that distance. And for optimizers, how do we do that? When we calculate, derivatives and so forth, we use this stochastic gradient descent or SGD optimizer that we've seen in the past. We're not using any metrics here. We're just trying to keep it simple for output, and that's basically our model. We have a model.summary here in JavaScript that we'll see in the console log how it looks like. We have our x's, we have our y's. And then we call this do training model that now I think will make more sense. So let's see what does this do. So what it does is calls the method fit with the x's and the y's. It runs for 500 epochs, which is a long time, or a lot of epochs. And it uses a set of callbacks. And if you notice in JavaScript, everything is a mapping or a dictionary. So it has curly brackets as well as has a key value pairs. So in this case, the key is epochs, the value is 500. The key is callbacks, the value is an inner mapping or an inner dictionary. That one has on its own key on epoch end, and the value is this method here that basically plots on our console, on the developer console, the epoch and what is the loss at the end of each epoch. So some basic monitoring basically of how our model is doing, and our goal is to see this loss function get lower and lower as we progress. Great, so again, we have our model, a summary, we have our inputs, we have our outputs, we have our do training model, which calls the model.fit. Once that is run, that means training has been completed, then we can do something else, which is basically prediction. And we call model.predict. We need to give it a TF.tensor as input, a 2D one. And in this case, we're just giving it a single number, 10. And this is a single number and a single record, so it's a 1-by-1 shape. We alert will just pop up a box for us. We can also console log the output as well. So let's see, the input is 10, and if our model is trained correctly, then it should have learned the relationship of 2x minus 1, so it should have been 20 minus 1, 19. It should be close to that. Cool. So I'm going to go to my first.html here, that it's loaded from my local folder. I will refresh this, and I will also open the console log so you can see here how things are progressing. And let me see if I can zoom in here. I'm sorry. So let's start from the beginning. If you remember, we had a model.summary statement here. And what that did is it gave us a basic summary of our network here. So we have how many layers we have. We only have one. How many parameters? 2. It has a bias and a weight and a bias. Total parameters 2, trainable 2, non-trainable 0. So basically we're trying to learn the W and the B here. And then if you remember this callback of after each epoch, we're printing the loss. We're printing the epoch and the loss. In the beginning, the loss is 0.8, 0.7, 0.5, 0.3, and then it kind of slows down 0.2, 0.1. So after 100 something epochs, we're still in 0.14, 1.3, still in 1.3. So as Lawrence calls it, the diminishing returns. We are basically training it for so long that we're not getting any significant improvement. So after 500 epochs, the loss is 0.1365. And then the prediction for the input 10 is actually 18.9. So we're very, very, very close. Obviously, there are multiple things we can do here to get this right, but this is just an introduction to how can we train a model in our browser. Again, this is running on our browser, so it's really interesting to see run. I'm going to pause here for questions, comments, feedback. There's a lot of concept covered here. Feel free to unmute yourself. Or if anybody is interested in the chat.
How large it needs to be the size of the data for this to work quickly enough?
So the training data, as you can see, is very small. I mean, just 6 elements. And how large can it be? You'll see examples later where we work with, I don't know, 5,000 records, maybe 10,000 records. Again, the more records you have, the more resources your browser is going to use. So you don't want to go like hundreds of thousands or millions of records. You might actually crash your browser. But we haven't reached those limits yet.
Okay. Okay.
And I'll say we'll see later on there's ways of handling large sets of data wisely in ways that you don't read it all at once. You only read what you need at that moment, and you can do some batching and some techniques to handle large data efficiently.
Yeah.
Okay.
I also try to keep track of, remember when I told you when the input was nonlinear, I added 2 versus linear. And when the input was nonlinear, I got an output of 18.90. When it was linear, it was 18.97. As well as the loss for me was way lower when the input was linear. So the loss was like 0.07 versus when the input was nonlinear, it was 0.13. So obviously, our simple neuron, which is basically a linear model, is trying its best, but our inputs are not linearly correlated, all of them at least, not all the XY pairs. I found that interesting. Cool. That was a very simple example. Next, for this next example, before I hand it over to Robert, we'll cover the iris dataset. And if if you work with machine learning, this is like probably the most popular data set out there, where you have to classify in this case, a structured data set. This is not an image. You're looking at a structured data set. So you're looking at the sepal and the petal length and width in centimeters, and you are trying to classify it in 3 classes: setosa, versicolor, and virginica. So let's look a little bit of how this data set looks like. So we'll be working with this iris.csv data set. This is our input. And again, the headers are here. We have our sepal length, width, petal width, and the species, which is in text. And we have about 150 examples here, 151 with a header. And our goal is to give an input, a structure input like this, for example, a combination of lengths and widths, and our model should predict the class, one of 3 classes. So as you can imagine, a simple neural network here with 3 units in the end and a softmax activation function will do great. We can start with a simple model. We don't have to build a very complicated one. So let's see how we're going to proceed with this. Again, I'll start from the bottom. So we have an HTML and a JavaScript code here. And the JavaScript, all it does is it's calling this method run. That's a little bit more for us. And let's see what this function run does. Again, we're going to import TF.js always. And this one, again, is an asynchronous function. This is the first time that we see where we are importing a CSV file, and we're going to see how we do that in our browser. So to do that, we're actually going to need that web server that I mentioned in the beginning. That web server will be basically handling the request from the browser for this iris.csv. It's going to look on our local file system. It will find that iris.csv and it will report it back to our browser. So let's assume for now that we have access to it. Then we'll use this TF data that David mentioned before, a .csv method. We're going to give it the URL, and we'll configure what is our label. So if you remember, we had 4 inputs. The 5th input, or the 5th column, was the label. And the 5th column was called species, if you remember. So all we're saying here is that everything else is data or X's, and the last column, the species, is our label, the Y. In terms of features, how many features we have, we can dynamically calculate them. We can look at the column names, how many we have. We can take their length -1. So in this case, will be 4. Samples, we're just hard coding it here. Maybe there's a better way to do this. Just 150 samples. And the other thing we're going to do is we're actually going to convert this data a little bit. We're going to keep the X's as it is. But for our Y's, we need to one-hot encode them, right? So we need to give, instead of text, like you see here, we need to give a triple binary code. So 100, 010, or 001 based on if it's setosa, virginica, or versicolor. So if it's, for example, setosa, we're going to look at this ys.species. If that is true, then this first entry of this list will be 1. Everything else will be 0. So this will be 100. If it's virginica, it will be 010. And if it's versicolor, it will be 001. This is a very elementary or simple way to do one-hot encoding of our labels. I'm going to return those as these X and Y pairs. That's our converted data. We're also going to batch them in batches of 10 records at a time so that we don't give all the records at once to our model and then update and learn, but we're going to break it down into smaller chunks of 10 records. We're going to build, again, a sequential model. Let's see here, we have a dense layer. Input shape is number of features. If you remember, number of features is 4. Width, length, width, length. And the activation, we're going to use a sigmoid here as a hidden layer with 5 units. And for our output layer, we're going to use a 3-unit dense layer because we have 3 classes. And we're going to use softmax. We need our model to output one of these 3 units as high as possible and the other 2 as low as possible, corresponding to which class it is. This is now, we're going to use a slightly different loss function. We're going to use a categorical cross entropy because this is one hot encoded data. And for our optimizer, we're going to use, instead of SGD like before, we're going to use Atom. And we do that with TF.train Atom. We can also specify a default learning rate here, sorry. Great, so we have our model. The other thing we're going to do here is, we're not going to call fit, but we're going to call something called fit dataset. This is another method that TensorFlow.js has. And that will take as input our structured data here, our converted data. We're going to run for 100 epochs. Very simple callback like before. We're going to just output the epoch and the loss. We're going to output here just some text. And then for testing, remember we need 4 numbers as our input, x's, and this is it. And this is a Setosa one, and this is a 1 by 4. We're going to call model.predict with our test value, and we're going to find out of the prediction, which is a 1 by 3 output, which is the maximum one. And we're going to take that index, we're going to look at the class names, and basically we'll map that index to which class it belongs. So if it's 100, this class name's p index will be Setosa. If it's 010, it will be Virginica. If it's 001, it will be versicolor. Cool, so very simple DNN here. And let me open my tab here. This is me looking at the fit dataset and fit. Cool, so this is the iris classifier. I'll right click, inspect to open the developer tools. And I'll refresh it just to make sure that this is running again. So there you go. Oops, sorry, I forgot to run my, so this is a good point. I'm not running my web server, that's why you don't see anything here. So let me start my server, and that is under Chrome apps, under web server. So as you see here, it will start this pop-up. I need to choose a folder that will render, that will basically access my files locally. So let me use week 1. Let me use actually the entire week 1, doesn't matter. Actually, let me use week 1 examples. There you go. Because that contains the iris.csv that I need. Cool. So now all I have to do is click on this again. And you see here, now the model is training. Zero 0.3, 0.4, 0.3, 0.4. This is a multi-class classification problem. So you see it's maybe some batches are easier to train than others. That's why the loss is not monotonically decreasing. Great. So we gave it a Setosa input, and this is the output of our model, 0.99 for the first neuron was outputting 0.99, and the second one, something very small, the third one, something very small as well. We can do maybe another one instead of this. Let's do one with versicolor. Save it. There you go. And refresh it. So there's no HTML content. That's why the HTML page here is empty. Everything is happening in JavaScript here in the back end. So this looks like a little bit interesting, okay. 0.3, 0.31, 30, 29, versicolor. Okay, perfect. So you see here, the last one is the versi color, and that's actually what we had as well. Cool. I will pause here for any comments, questions. But as you can see, we built a very simple DNN that takes a structured data set for features and is trying to do multi-class classification on those features and tell us which of the 3 classes our input belongs to. I will stop sharing here and let me know if you have any questions, and in the meantime, I'll hand it over to Robert.
Thank you, George. Are there any questions on the materials that we've just gone through? All right, well then we'll move into week 2. I will share my screen. Share the whole desktop. And come over here to Chrome. Okay, can you see my screen?
Yes.
Excellent. So now we'll be looking at week 2. Week 2 is called Image Classification in the Browser. And we'll be looking at computer vision problems this week. There's a couple different sections. There's creating convnets in JavaScript. There's using a sprite sheet, and a little bit on the classifier itself. So my takeaway from this week was we're basically going to extend a lot of what we learned during week 1. And I'd say there's 4 big new things in week 2. First of all, we're showing how to do convolutional neural nets, whereas in week 1 we did dense nets. Secondly, we're showing a new method for data acquisition, which is this sprite sheet that I'll discuss a little bit further later. The third thing we'll discuss here that's a new thing for this week is the TF.js viz library, which is this video right there, or reading rather. Will give us a new way of visualizing the training process, the loss accuracy, and the fourth thing that we'll be doing here this week is some interactive data entry into the browser, or interactive data entry using the browser to create test examples for our trained model to classify. So I'm going to take a look at the code. I've been using Visual Studio as the editor for this one. And what we'll have is a directory of 3 files, and we are going to be looking at the MNIST dataset this time. This is the dataset with, I guess there's 65,000 examples, and these are very small images of digits, 28 by 28 pixels. And this one has it's just black and white, no color channel at all. So the image size is 784. So again, we'll have an HTML file that wraps around everything. We'll be calling TensorFlow latest version in that HTML file. We'll also be referencing this new this library, TF.js viz. And we'll draw a few things here, and we'll be referencing these other 2 JavaScript files, data.js and script.js. So the meat of the process is going to be down here. So we're doing a short run function at the end again, and we are, first of all, we're going to load a class mnistData, and that class is going to be defined over here in the data.js. And you can see that this class is actually goes from line 38 down to, I think it's the entire, yeah, it's pretty much the entire file. Is just defining this class mnistData. And the idea here is we want to fetch the data for these 65,000 images in an efficient manner. And one of the challenges with doing this efficiently is, if you recall from week 1, I'm not sure if I don't remember if George discussed this, but when you're loading the CSV data, one must do it through an HTTP protocol for use here in TensorFlow.js. And one could think that the easiest solution for training with a bunch of images is to have a folder full of images, and you would call each one and batch them together, retrieving them somehow. But it turns out that that would add a lot of overhead to a lot of unnecessary back and forth HTTP requests. And there is a more efficient way to do this, at least since you know what the data set is that you're looking at. So what you actually have here, this sprite path, mnist images sprite path, is equal to storage Google APIs mnist images ping. And if we go over here to that link, we don't see much, but you can kind of see this faint line down the middle. And then you zoom in, and now you've got a bunch of something that's not really comprehensible. But what we're actually looking at here is one massive black and white image. So each row in the image corresponds to one image in the mnist data set. So it's going to be, for 65,000 images of digits, we're going to have one row of pixels for each one. And then going across here, we have 784 pixels, 28 by 28. So you can kind of see how this looks like bands here. What we have is like the 28, I'm not even sure if it's rows, which way it's organized here. But we have essentially 28 columns of data that correspond to the 28 by 28. So 784 across here. But if you recall from the mnist, I'm not sure I have that up in a file. I think this one might be a good, yeah. mnist images look like these ones we see here on the right. So you'll have black and white images. Typically you'll notice that the white pixels here are in the center of the image, that the boundary pixels almost never get filled in. So that's why you see very little activity out here on the edges. But in the center you have, you can see a lot of filling.
So Robert, if I remember correctly, each row is a flattened version of that 28 by 28 image. So each row of this image is actually a flattened version of the original image. So that's why this would be 65,000 rows by 784.
Yeah, what I can't recall is whether these first 28 pixels over here, do they correspond to one row of the original image or one column?
Yeah.
It doesn't matter.
For a moment there in the beginning, I thought we were in the Matrix looking at this.
Perhaps we are. So that sprite path has been defined up here. Oh, and of course the other thing you're going to need is the labels. So each of those images has a label, and these are just uint8. This is actually interesting. There's the labels are stored in rather inefficient fashion. It's using 10 bytes per image to store a label, even though you really technically only need 1 bit. or I'm sorry, you need you could do it in 4 bits, right? There's only 10 possible labels for each image. So at this point, the rest of this we see here, the MNIST sprite path is loaded here. Just a lot of code in here for chunking the image. My understanding is that we'll see much more efficient ways of doing this. This is all kind of done by hand here this week, and this was not part of the exercise. This was just provided as boilerplate code, so I didn't go through this in too much detail to follow it. But the other important aspect from this class is that it defines a couple of methods, next train batch and next test batch, as well as next batch. And this is just a way of passing the data out of this class and returning the indices pointing to the correct spots in the sprite to look at. So in summary, this whole file here is data acquisition. We'll return to the script.js.
Do you mind zooming in just a little bit in case people can see the code?
Zooming in. How do I do that?
Control plus or Command plus or View. There you go.
Is that helpful?
Yeah, keep going. One more.
Oh, further?
There you go. Perfect. Thank you.
That's good.
All right. So we'll go back to the bottom of this file here. New MNIST data. We've got our data loader, and we're going to run this as an asynchronous function, as well as we saw in the data.js. And now what we're going to do is define a model. Constant model equals getModel, and we've got that at the top of this script here, function getModel, and we're returning a model down here. And for those of us who have done the other TensorFlow courses or worked with TensorFlow in the past, this should look pretty familiar, even if it's now in JavaScript rather than Python. So you're going to begin by defining a TF sequential, just as we did in week 1. But now we'll be building a convolutional neural network. So we have a conv2D layer, max pooling, conv2D, max pooling, flatten, dense, dense. And here we have input shape. This is the original image, 28 by 28 by 1 color channel, kernel size 3. We're going to start with 8 filters, ReLU activation. One thing we can do here, actually, if I can move this over a bit. So if I move my browser over here into this one, you can see the model summary right now to the right, correct?
Yes.
And now I'll try to come back over into here, and you can see these 2 windows on top of each other.
Perfect. Yep.
Okay. So we have our 28 by 28 by 1. This is, I guess, I had expected to do this with smaller text size, so you can see the the model here, but that's no problem. Conv2D, we get a output from this first layer of 26 by 26 because we're not padding. We have 8 filters, and that will be a total of 80 parameters. Parameters remember, is just going to be the size of the filter, which is 3 by 3. So that's 3 by 3 is 9, plus 1 is 10, times 8 filters is 80. And then we have max pooling layer next, which is just doing a 2 by 2, so it'll drop that 26 by 26 image down to 13 by 13. And then we have another conv2d layer here. And again, this one is a kernel size of 3 by 3. So with that kernel size of 3 by 3, we could do the computation similarly to verify these numbers of parameters in each case. We have max pooling, then the next pool size 5 by 5 by 16. Then once we flatten that, we're down to a 400 long vector, and we'll feed it through a couple of dense layers, and those dense layers will help us figure out which digits are which. We've got 10 classes, so our last unit here is our last layer, sorry, is activated by a softmax. The other thing that we do as part of the model definition is we're going to compile it. We have the optimizer is tf.train.atom, and we don't need to feed any parameters into that one. We're going to use the categorical cross entropy loss, which is standard for a multi-class classification problem. And then we're going to use a accuracy metric because we want to know what the system accuracy is. So now that we've defined the model, we'll return back to down here. And this is the code that's showing the summary that I just displayed at the last time along with that code. And then we're going to do another asynchronous function here, which is training the data. Again, we want to do this asynchronously because this is going to be a slower training process. And we want to not make the browser inaccessible while we're training. And that train function is defined up here, async function train. Now we're going to use the TF.viz, which we had talked about earlier. Let's go back to Chrome here. And this is all part of TF.viz, actually. We're visualizing the architecture here. Note that this is in contrast to what we did during week 1 when we were leveraging the developer tools to get a sense of how our model was training and get a little bit of feedback from our code. But here we have taken advantage of TF.js-viz, and we're going to get some figures here that are going to tell us how well the training is going. So before I go into that, I'll describe, well, no, we'll go to TF.js-viz. We'll introduce the library. This is, I think, the course, this page right here, the TF.js-viz documentation, just leads you directly to that GitHub repo, and that's this one. And you can see that this library actually has a lot of capability beyond what we're doing with it this week. We get some screening shots for training metrics. That's what we are doing this week. We'll be using the show.fit callbacks method. But there's also a number of evaluation tools. One can look at the accuracy, look at the confusion matrix for each of these things. So we could look at our 10 digits, look at the confusion matrix here. And we can get some model internals as well. Model summary, which we already saw. We can get some frequency distributions of the weights within each of the layers. And then we can get some visualizations of the activations as well for various filters at each layer. So here we have a model where they've trained with an input of the digits that are input here show up over there. And the first layer is I guess that's the second layer they're showing here. This page that I have open here as well demonstrates the first layer also. And the first layer, you don't really see too much, doesn't look too different from what the original image did. You are just running these filters here. And if you can see the filters, they're not the edge detectors, or they're not the obvious examples that you might expect the model to be looking for, like edge filters or particular shapes. But this is just what the model has learned here over, I think they trained it for 10 epochs. And I think our model will be training a similar network, not identical, but a similar size network for 20 epochs. So that's the layer 1 activations. Then you get into layer 2 activations, and they're going to look a little bit less easy to figure out what's going on. And then we get some information about the dense layers down here, and now we get some distributions over the dense activations. So we're looking at some sample images here on the left. Here's an 8, another 8 down here, but there's some other digits in here. You can see which of these images are classified very confidently. Which of these images are missed entirely, like this 9 here is classified as a 4. Looks a little bit like a 4 maybe. And then here's a 4 that's not too surprising that this one's not confidently classified. It's got some uncertainty in a variety of digits. So for the model that we're doing in the course, we're not actually displaying all this stuff, although they do show you here how you could do it. I just haven't implemented all of that. But what we do implement in the course is a very simple model training, loss, accuracy, loss and val loss, accuracy and val acc. Now, one thing I noticed I had to do to get these to display correctly, and anybody who is wanting to go back and work through the GitHub code should make this change as well. But I believe the version on GitHub uses the words accuracy and val accuracy in here instead of acc and val acc. So you have to put accuracy up here under metrics for compile. But for the fit callbacks function, which we're using in TensorFlow viz.show.fit callbacks, the metrics here that we pass it, it has to be acc and val acc, or else it won't be interpreted. So just a little bit more on this fit callbacks. What it's doing is it's saying, what kind of container are you gonna display it in on your HTML page, and what are you going to be displaying? Loss, val loss, accuracy, and val acc. You pass those as arguments to fit callbacks. And fit callbacks is documented over one of these windows. I think it might be the one that's behind there. Yeah. Fit callbacks under TF.viz.show. It shows you a little bit of how to use it, but it essentially runs on batch end and on epoch end. You can use it. So recall that we'll be doing batches and training intermediately within each epoch, adjusting the weights. Any questions on what we've covered so far?
None in the chat.
Thank you for covering the library, Robert. I like the features that it has, really interesting ones. And since this is in JavaScript, it's so easy to show it on your browser, right? It's interesting.
Not sure I heard all of what you just said. Can you repeat?
Sorry, I was saying that thanks for covering the library. That was an interesting one. I like its features.
Yeah, and it obviously has a lot more capability than we're using right here. but it's good to be aware of it and know where to look if we want that capability in the future.
And thanks for putting out the ACK versus accuracy. I was wondering why my graphs don't match the ones that the course had.
When you say your graphs, are you talking about the ones from week 1 or the ones
From week 2? I was using accuracy and val accuracy instead of ACC.
Mm. Yeah, I think that changed at some point. I think it used to be accuracy, and they just didn't update the source.
It looks like you had to put the parameters in the code, right? And that produces an output. Can you, is there a way to put the parameters, let's say, in on the browser, and that goes into the code executes, and you get the outputs?
There will be a way to do that. We're not going to get there this week. What we will do this week is create test images to feed to our model, and we'll be doing that interactively in the browser. But essentially, when we do that, we're just reading data into a tensor, as I'll show in a bit. Great. Okay. So batch size here is 512, and train data size is 5500. Test data size is 1000. And what we're going to be doing is getting the next batch within the train data size. So what the train data size is doing is it's actually down selecting from the original sprite image, I believe, which had 65,000 images, and we're only using a fraction of those. And then within that, we're going to be batching it down to 512 images as well to send to the model for each training step. One other thing that they do introduce this week that I had not mentioned yet is this function TF.tidy. And that's a pretty useful function here when you're passing a lot of data around. And let me show the doc on that one. I think that's this window here. Yeah. And the idea here is it's basically a smart garbage collector. So it's executing the provided function. You actually pass it a function inside TF.tidy. That's what this parenthesis with the equals arrow is. And eventually it's going to return something in that function in the example here. But the idea is to clean up as much memory as we can and free up everything that this function is using except for what it needs to return. So in our case, going back to Visual Studio, we will be getting this next training batch and then reshaping it into a new tensor, but discarding the original D variable so that we don't run into a memory leak. Not sure how necessary that is for this example, but another useful technique to learn about to enable more efficient data processing. Finally, at the end of this train function, we've been going through the train function now for all of this fit callbacks, tidy data acquisition. And now we get the model fit, and this is going to look a little bit like the TensorFlow version again. You pass it your x's, you pass it your y's, and now in JavaScript we end up passing essentially a bracketed list of key value pairs for each of the parameters, whereas in Python you'd have batch size equals something. Here it's batch size colon, and it's all wrapped inside these brackets. But the arguments look very similar to what we would have run in Python. We have 20 epochs we're going to use. We're going to shuffle the data, and we're going to have our callbacks point back to this fit callbacks function or constant that we created back here. The remainder of the functions defined in this script.js are for setting up some of the interactive graphics that we're going to be looking at. There is a save function here, which we're going to look at. So tf.browser.fromPixels raw image. And here what we're doing is we're setting up an example where we can train. We've already trained in the browser, but we'll be able to pass it new examples in the browser. So I'll go over here. I've already got this model trained. And I did so using the same web server for Chrome that George had mentioned earlier. You've got to start the web server, point it to a folder, and run your web server URL. Copy it, paste it up here, and now we have our handwriting classifier. So the visualizations that we had created through the fit callbacks are shown here. On batch end, we get a loss and an accuracy, and then at the epoch end, we get a loss and a val loss, accuracy and a val accuracy. So you can see this model is training MNIST to roughly 95% accuracy. I think there's a, yeah, you can move the mouse along here and get a little bit of interactive info as well. Same up here. And then they put this little box over here. And so what you can do with this is draw an image and see if you can classify it. So I will say that my artistry skills with a mouse are even worse than my hand drawing, but hopefully I'll be able to scribble a few numbers into here, classify, and we get a message saying that we are classifying this digit as a 1. And then I added another window here which gives you the softmax output, so it's extremely confident that it's a 1. And that's one thing that I noticed with this model. Now I will say that I modified the original code a little bit here. Originally it just had alert p index, which would have printed out only the predicted class, but not the full softmax output, the full 10-dimensional tensor, or 10 valued tensor. So what we're doing here is we're passing in this raw image that we just created by drawing in that box. It's resizing it to 28 by 28, passing that into our model, running a prediction on that tensor, and then once we have the prediction, just determining which class it is by running a tf.argmax, whichever softmax unit activates the most, and then you can alert on both of these values. So I added the alert prediction. The original code only gave you the class. So one thing I think our model has overtrained a bit, you don't see the val loss decreasing much. In fact, it might even still be increasing here at the end. See if I can back in this window. So I don't seem to be able to mouse along and see those numbers here anymore. Maybe
You have the
maybe I have to close that. Yeah, that's what it is. So you don't really see a ton of deviation yet between the training and val performances here.
Mm-hmm.
But one thing that I did notice in trying to classify my own handwriting here is that it's very difficult to come up with an example that it doesn't classify with 100% confidence.
All right.
Robert, can you try a couple other examples? This is really cool.
Yeah, please.
Sure. So one example you can try is just like one with no pixels lit at all,
Ooh.
and it comes up with a 1 on that. That's interesting. I thought I ran that one earlier and it came up with a different number. And I don't think I've retrained the model since, but we'll find out. So I'll draw. So it thinks that's a 9. So one thing that I am not sufficiently dexterous to do is make my handwriting in this thing look like the images that were in the original MNIST set. These numbers are clearly out of distribution. So definitely the performance on the digits that I try to draw in here is worse than it is for the test set.
But that makes it more interesting.
Yeah.
It does. But then it also classifies this with 100% confidence too, which is maybe less interesting. I was kind of hoping to see some mixed values. I think I've played around with this and tried about 50 images, and only 1 or 2 of them showed anything other than unit probability for the chosen class.
Can you try a letter, something that's not a number?
Sure. Three.
Are you
With 100% confidence.
Are you putting the raw values, or are you putting the softmax version, or like the argmax version of it? Because often.
So I had that question.
Yeah, you're doing argmax there.
Well, there's an argmax that's
I
the
see.
P index is being computed as an argmax,
Predict. Okay.
but the prediction itself should be the raw output of the model.
Okay. Then keep trying.
Unless this is somehow using the same memory here, but I don't think it is.
No, I don't think so.
But you did see some cases where it wasn't 1.
I think I saw 2 cases where it wasn't unity, and they were both very close, like 0.99.
Keep trying.
So I mean, I think when you do train models too long, it tends to get really overconfident on the predictions it's making. So you might have, let's go back to, yeah. So the numbers in the distribution it's doing all right on, but if I can draw, classify, okay, that's a 2, 100% confidence. But I tried drawing some kind of random stuff in here too, like classify 8.
That's clearly an 8.
And still 100% confidence. 9. That one I would think would be a better 8. That doesn't look too far out of distribution, but it misses that one.
Hey, Robert, I don't remember your training images. Were they bigger? Do you need to draw a little bigger?
That's a good point. Maybe they came closer to filling up the whole box. We could try something like that.
So one thing that is happening here is that this canvas is 10 times bigger than the 28 by 28. This is 280 by 280. And you're doing.
Yeah, and then it's down sampling it, right? It's resized bilinear, I guess, from the raw.
Yeah.
To 28 by 28.
So 9 is a tricky one, and 4 maybe is a tricky one, or 2.
Yeah, 4 seemed like it might be on the tricky side.
Ooh.
I also had some challenges with 5s, I think.
What about 6?
Try that again. 5.
Close.
But yeah, what I think is happening is when you train the model beyond the point where it's getting most of the training examples correct, then it's just further training just increases its confidence. So that may be why we're getting such confident predictions. Although it is still missing, what, 4%. So two. I see a bunch of, let's see, comments in the. Is there anything in the chat that we should address?
No, Ted was asking if you have any dropout or other regularizations in this model.
There is no dropout, no other regularization in this model. That's correct.
Robert, I was trying to understand the x-axis of the batch chart.
The x-axis of the batch chart.
Yeah, so it's around, what is it, 220, 219?
Where are we looking on batch end here?
Yeah, what's the very last one? Where did that number come from? Like, I was trying to figure that out.
Yeah, so what's going on here is that each epoch, it's processing through about 5,500. Remember, we selected 5,500 training examples. That's all we're doing each epoch. And the batch size was 512. So one epoch is worth, what, 11 batches. So that's why you have 220 batches here over a course of 20 epochs.
Yeah, okay, I see, that's right, 10.74.
And that comes from these numbers right here.
Perfect, okay.
12 and 5,500.
And this is just a subset of the entire MNIST dataset, right?
Yeah. Although when I said that, I'm not actually sure if it's just getting 5,500 images from the sprite each time, a different 55, or is it just getting the same 5,500? This is next train batch, train data size, but I think if you go back and look at this code, which was all canned for us, it might be shuffling this somehow and getting different images over a batch.
Couldn't tell. Okay.
So one epoch is giving you 5,500, but I'm not sure if it's the same 5,500 each epoch. Remember that this is an async function, so it's loading it, I think, while it's training. It's loading it each time it needs a new batch.
Cool.
See, I think it is, there's a shuffling going on here. So I think it is probably using the entire train set somehow. It's just not using it all each epoch. So, unlike week 1, the week 2 exercise doesn't really introduce anything too new. We're dealing with fashion MNIST in the exercise there. And similarly, we'll be loading it from a sprite. I think this is the fashion MNIST sprite. One difference is it's a little bit more populated out here at the edges. And it seems like there's some structure in the orders of the classes, right? They're not randomly interspersed examples. But again, we have 10 classes, and the exercise for this week is to essentially reproduce what we did with the MNIST digits. So I think we'll just leave it at that.
I can maybe talk a little bit about the exercises because I didn't mention at all the exercise for week 1 and for week 2. Maybe I can use the GitHub repository, which.
Sure. Yeah. Why don't I'll stop sharing.
Cool. Thank you, Robert. Any questions for Robert in the meantime? This was a very cool exercise in the end. I really liked it. Where you draw a number.
Very good, yeah.
Okay, share screen. Some articles about sprites, but before I talk about that, so the exercise for week 1 was you wanted to build a classifier that again was taking structured data.
You make that bigger.
Yep. And that structured data is coming from, I think, medical applications of the size of a tumor, and if based on the size of it, some specific metrics, it's a benign or malignant tumor. Let me look at maybe the train CSV. Let me see if I have it here open. So I think 0 means benign and 1 means malignant. So we have like mean radius, mean texture of a scar or tumor, I think. The mean perimeter, mean area, smoothness, compactness, cavity, and so forth. So you have all these metrics, all these fields, and the goal for week 1 exercise was to build a classifier that outputs 0, 1 based on this labeled data.
Yeah, it looked to me like there were 30 features there. 10 of them were mean measurements, 10 of them standard error measurements, and 10 of them worst of the same 10 metrics.
Mm-hmm. And then for week 2, as you mentioned, you are supposed to build a classifier for this fashion MNIST data. And sorry, let me open the exercise. And you see here, this is like the skeletal code. You're sequential. You're supposed to build your network here. You're supposed to build your metrics, container. The training size for this was, again, a subset of the original data. You don't want to overload your browser and so forth. And these were the classes, which was really interesting. I think, do I have this still running? Let me see if I still have this running. I want to give this a try. Sandal. So let me look again at, so we have t-shirt, trouser, pullover, dress, and so forth. So let's look at this data set again, right? We've seen this in the past. So let me see, maybe I can make a bag. I think I can make a bag, but I'm not sure. This system is recorded, so let's Let's be brave and make a bag. Please be a bag. Not even close. Maybe a shoe. Is it close like I come to a shoe? Sandal. Ah. What is the easiest thing I can draw here? Pants.
I had some success trying to draw the ankle boots.
Ankle boots. Ankle boots.
The ones at the bottom.
Oh, this one? Okay. I don't know if I'm such a good drawer of ankle boots. Like sandals. I don't know why. Cool. This was an interesting one, yeah, as well. I briefly wanted to mention this idea of sprites, that it's been used extensively even in the past. I don't know, when computer games were first introduced, that you don't want to make too many HTTP requests. So here's a sprite, for example, of multiple flags, and then you can navigate it. You can pick different flags for different countries. I found this article from 2009 really interesting. It's a very old one, but it had some examples. For example, this is from Pokemon, the game. So first of all, the images don't have to be the same size. You see here, there are different sizes and shapes. You just need to know how to parse this larger image into chunks. Here's some other examples that I find interesting. This is from, I think, Amazon back in 2009 was using sprites for different size and different variations of their logos. At some point, Apple was using them as well. YouTube for like or stars. This is 2009, okay? So going back in time here. CNN, Dig, Yahoo or YouTube, Google, not sure what Dragon was, TV1, and so forth. So it's an existing concept basically that's been used successfully from other applications as well. Sorry, this one had a nice one as well with like an animation. You can make it for video games, and you can pull basically if your actor is or agent is like walking, shooting, or like falling down. I found that interesting. Cool. That's what I had to share. I'll stop sharing, and I think I'll hand it over to David if there are no more questions from me or Robert.
I have a question for both of you. How familiar were you with JavaScript before this? I mean, did you use it a lot already? Or so how accessible is the course if you're not familiar with JavaScript?
I have very little background in JavaScript. The course is designed to be accessible to someone who's familiar with the TensorFlow in practice Python material, but doesn't know any JavaScript.
Okay, good to know.
Yeah, I had a little bit more. I had taken like web development courses in the past, and I've used a little bit of web development, but it's mainly programming. The one thing that I don't super like about JavaScript, that if you have a typo or an error, it's not super helpful where the error is. For example, when I was working on, I think week 2 on the exercise, the way that I was defining some data, it was supposed to be on a list. I did not define them as a list. I gave them as comma separated entries, and it was giving me an error on the TF.js library, which was not the case, right? The case was with my code. So it took me a while to figure out that, oh, the way that I'm using the data is wrong, and that took me a while.
Okay, thanks.
So you're saying that error diagnostics are a little more difficult?
Yeah. In this case, for me, yeah. Syntactically, it was acceptable, but in terms of interpretation, it was wrong. Like, See if I
That
can,
makes sense.
yeah, if I can find that example, I can share it here.
You want to share it? You got it?
No, I'll put it on the chat. Don't worry. Oh yeah, it was in the reshape. So at some point, where's the chat? Yeah, I'll put it in the chat. At some point, you need to do a reshape of your data, right? So it needs to be the training size 28 by 28 by 1. So if you ignore this, if you just enter this, I don't know why I did that.
Oh, on the list
It will
inside.
work, but you'll get an error. The code will not work. Sorry, the page will hang, and it will tell you have a typo or an error in TF.js, some line. I was like, why? That's not true. That's what I kind of dislike. But on the other hand, you have so many cool visualization and access to camera, mouse, audio. So I'll take it.
Yeah, I actually found the developer tools to be pretty helpful. Just having that console and relying on the novice programmer's standard trick of just putting print statements all over the place to figure out where the error actually is.
Yep.
Yeah.
David, you asked if you can hide the architecture. Yes, there's a hide button when you do the TF.js. But if you hide it, you cannot bring it back.
Oh, there's no return, huh?
Yeah.
Okay. Yeah, we can look at that later. All right, friends, any more questions before we wrap up?
Hey, I have one quick question. It's kind of a little out of scope of the course, but it's something that I'm wondering now, seeing this. Do any of you know if it's possible using JavaScript? The JavaScript you've done training and inference. Is it possible to utilize a GPU for any of this from JavaScript?
Not on the browser, I would say.
I don't know. You'd have to have access to one somewhere. I know that I'm just running on my CPU.
Okay.
But Lawrence,
So next week, we will talk more about training your model somewhere other than the browser, and then saving that model and bringing it into your browser to do inference. So at least you can do the training on a GPU somewhere, or
and also Lawrence mentioned this WebGL layer, right, that modern browsers have, and I think that gives you access to the GPU of your computer. I haven't seen it yet in this first 2 weeks.
Yeah, I think he was indicating that could be used with Node.
Okay, it's a great question, Neil.
I'm not sure if it was useful for browser though.
Well, I mean, like these models.
Oh wait, yeah. I think that was for a browser. WebGL you could use to accelerate.
These are really small models like the MNIST, so you don't need it. But if you wanted to do something fancier, I guess maybe the idea is that your web browser is sitting on a light client like a Chromebook or something, and you do your heavy duty stuff somewhere else. But just wondering.
We'll have to see. It's new for us too.
All right. Well, as I mentioned, next week we're going to continue this, and we're going to get into on Wednesday. We'll join us again. We're going to talk about week 3, which is going to be converting models to the JSON format, and week 4, which is using some pre-trained models and doing transfer learning with TensorFlow.js. So we hope to see you back on in a week's time, and great to have you join us, and we'll look forward to that. I'll stop my share. George, you wanna... turn the video off, turn the recording off, and we're good to go.
Yeah, yep. Thank you, friends. I'll stop the recording here and I'll leave the session open for discussion. For all of you join us on YouTube, hope to see you next time. Thank you, friends.